that will go up. I think I'll put it like under Twitter and doc sharing. So this class won't meet Friday, but your other classes meet Friday. On Friday, I'll be out of town, but the Woody Observatory will be open for public viewing. They take great care of you if you go. An awesome telescope. We're going to talk a little bit about telescopes today. Then Monday and Wednesday we'll need to finish off Unit 2 for your exam. Actually, instead of the 23rd, it's going to be the 25th. So September 25th. Any questions about all that? So we'll see how far we get. We're still on Chapter 5. Part of the reason we need to talk about the structure of an atom, I know it seems kind of strange for astronomy, but actually we are able to understand the nature of stars, we'll talk about more later about stars, based upon what electrons are doing around atoms out there where the star is. Okay, so that's just kind of hopefully a teaser. I actually was talking about atoms in my other class this morning, and what works well is using a BB for the nucleus, the center of an atom. And like what we talked on Monday, we said in the nucleus there are protons and neutrons, and then the electrons are outside the nucleus. So what gives us this information about stars are what the electrons are doing. Not just about stars, but the electrons are doing this right now. Okay, electrons around atoms are doing this sort of jump that we're talking about. So electrons actually, back in, gosh, I don't know what year it was, the mid-1900s, they understood that electrons actually are doing something more interesting than just being a cloud of electrons. Electrons are actually hanging out at what we call different energy levels. So what you'll see me do is I'll talk about the energy level of an electron here, and then here, and then here. Okay, that's where electrons kind of reside, and that's kind of how much energy they have. So space electrons and normal Earth electrons do this too. So electrons like to be couch potatoes. Electrons like to be hanging out in their lowest energy level possible. Okay, electrons can be promoted or transitioned to a higher energy level. And so I go like this, and then I go like this. So they're promoted. There's nothing in between for electrons to be at. They're either at state A, ground state, or a higher energy level, or even a higher energy level. This promotion, usually electrons can get excited and transition to a higher energy level based upon an energy, usually thermal energy. It could be electrical energy. A lot of light bulbs, the way they work basically is to take a thing of electricity and to zap the electrons to a higher energy level of the gas inside the light bulb. Then when they fall back down, they emit light. Okay, so this transition is important in what atoms are doing in outer space, and actually what atoms are doing here. What happens then is, you know how I've been kind of having a hand here for this energy level and a hand here for this energy level? This sort of jump is specific to the atom. Okay, not the atom, but the atom, not the atom. Okay, so this is how we understand we can identify elements based upon what sort of transitions we see. So actually there are three types of, I'm getting to the transitions, I'm going to come back to that. But based upon the transitions, actually there are three types of what we call spectra. This continuous spectra is just like the rainbow. If you want to put rainbow next to continuous spectra, you can. Okay? Basically what that means is what Newton found is you can pass white light through a specific piece of glass called a prism, and you can get all colors of the rainbow on the other side. Okay? Continuous spectra. This, though, emission line spectra, comes from electrons transitioning. Now, there are two types of spectra created by electrons kind of jumping ship. Now, do you see the word emit in emission line spectra? Okay, so if you think emit, you think of giving out. Okay, so actually, this sort of spectra, just kind of as I'm using my hands to show two different energy levels, this sort of spectra is created after, I should say, an electron has been excited. So here we go. Here's energy level 1. Okay, this is a lower energy level, and here's energy level 2. This is a higher energy level. In emission spectra, somehow, usually through thermal energy, an electron has been promoted to a higher energy level. When that electron falls back down to the ground state, then it emits a certain amount of light. That's emission spectra. And depending upon what atom, you figure that's an electron around an atom. So we have the nucleus here. Okay, that is an electron associated with an atom. Whatever that atom is will give a characteristic jump. Okay, so those are emission lines. Okay, they're bright colored, and we're going to see some examples of them. Absorption lines, can you see the word absorb and absorption? Absorption. So absorption lines are created the other way. So I'm going to go ahead and draw my two. I'm going to do this is the ground state, okay, and this is an excited state, right? And then, of course, we have the nucleus down here, right? So in this case, actually, an electron is absorbing energy to go up, to be promoted. That amount of energy that it absorbs to get up there actually will make a dark line on your otherwise continuous spectra. So this actually is absorbing energy. So I guess I could do it this way. I'll put an arrow here and I'll say energy in. Okay? And however big that jump is, it's going to make a dark line. A dark break, a dark line. Now, if you have the emission spectra and the absorption spectra of the same element, you're going to see they look like black and white negatives of each other. They're going to be the same locations, either bright lines or dark lines. So here's where, let's go ahead and, here comes the noise. This is, I think it might be neon. Okay? But in that, I'm talking over this, in there actually is a gas. Like I told you a minute ago, the electricity we're sending through it is exciting the electrons around that gas. Then those electrons are falling back down to give us emit light. It's a characteristic orange light, but if we were to kind of take that light and kind of smooth it out, we see all colors of the rainbow. So let's see if we can actually see some spectral lines for that, for neon. So these that I gave you actually are what you call, they have a certain aspect to them. So keep rotating it. Look at the light. Keep rotating it so you actually see some lines. And sometimes we have to kind of look on the side. I'm having to get closer. Where are they? I don't see mine yet. Oh, okay, finally. So the way I found them is actually to go about a palm's width away from it on the side, and I see my lines. Anybody else see lines yet? Put your palm up and go less than that here. Go closer. Yeah. Yeah, go closer. Now, like when you're viewing stuff, don't say you see it and you don't really see it. Get up till you see it. And you might need to turn it.
So different, man. Oh, I got a head mower. Yeah, man.
Yeah.
I see it now.
Oh, there, I have to do that again. So I see yellow, orange, and red lines. And we were to have a different gas, we would see different colors. Did you see it yet?
I see blue.
See a green.
I see blue,
Green?
a green.
But they're lines, they're not like a blur. It's like, did you see them?
Yeah, I see the red around.
Like red, orange, yellow,
Yeah.
space,
Yeah,
green.
those are bright ones. Oh, you see green too?
At the
Okay,
end,
gotcha.
put it around.
Perfect. Yes, that is it. I don't see green, but.
It's really faint. Might be blue. I don't know.
Actually, I see green before it. Yeah, I do see green. I see green before the yellow. And that brings up a good point. We talked about colors are different wavelengths. So basically, you see the short wavelength to the long wavelength in the spectrum line. Okay. Very good. Most annoying sound in the world.
Darker blue and then red.
You see it?
I see all of it. There's red, there's light blue, dark blue.
You see all of them? Oh, good job. No doubt. So actually, these oh, thank goodness. These things that you were using were called diffraction gratings. They're just basically a little piece of plastic that have fine lines in them that do the same thing that prisms do, separate light. So, are there any the other thing, I gave you a handout. Are there any questions about that handout I gave you? It's kind of cheesy. I wanted to give students an example of what I'm looking for in the lab write-ups. Okay, so the first page just simply kind of says what I did last night. Okay, the second page you kind of see, you guys will probably turn yours in, probably not electronically, but if you do turn it electronically, you can also, for this lab, you can take a picture of it. Okay, the sky map that I marked up. And then this actually are my cheesy pictures. Which again, if you submit these electronically, you don't have to print them out. Okay, so I just want proof that you did it. I was toying with how do I get a picture of me doing this lab. So I was asking my husband, he's like, well, put a flashlight on. So I did. I put a flashlight on me and took a picture of me doing this lab. Okay. So this actually is because in the past I've had students I know that have basically, 10 minutes before class, taken their sky map and circled some things and handed it in for lab credit. And I'm like, no, we need to do something a little more than that. Okay, so that's kind of where this is coming from a little bit.
So it's an A+ paper.
This would be an A+ paper, yes, yes. The other thing that I did before I wrote this up was to look at the teacher, which was me, my criteria. I have like a checklist of things you need to include in your lab reports for each type of lab. So I made sure I had that handy, and yes, this would be an A+. All those elements are covered. Okay? So you can't just take it and substitute your name and hand it in as yours. All right. On to the whole electron thing. So we have three types of spectra. The continuous spectra is like the duh spectra. But actually, I kind of tease, it's more than just giving you no lines, okay, no absorption lines or no emission lines. A continuous spectrum, here in a minute we're going to see that when we look at that we get a sense for temperature. So continuous spectra can give us temperature. So here's a picture of how a continuous spectrum would be created. Basically you have your light source there on the left, okay, just a portion of that light source is being run through a prism, that's what the slit is for. Then through the prism you see it separated into colors of the rainbow, just like Newton saw. An emission line spectra, now that's like your light bulbs, okay? That requires basically somehow you have to get a gas excited, okay? In space, in outer space, what that is you'll run into a nebula, which is a gas cloud, and it is actually heated, and so it's glowing, okay? And that glow is an indication of the chemistry or the elements that are in that cloud. So we call that kind of being rarefied. It's hot, rarefied gas, okay? And an emission line spectra would look something like this, okay? So you see kind of like we saw here with your diffraction gratings, okay? You saw those lines? Those are what those lines are, characteristic of what is in the gas. So it's awesome. We can actually look at the spectra of gas in outer space and understand its chemistry. One of the things about spectra is we actually have these two options. We have this option, which is the visual spectra, which you see. Again, you can actually see red, orange, yellow, green, blue, indigo, and violet. Okay? Different wavelengths. The other way to look at it is more, if you're like a number sort of person, just a graph. The thing down at the bottom is just purely a graph. What you see along the x-axis, what you see along the x-axis is wavelength, and what you see along the y-axis is intensity. So they're basically showing the spikes there at those different wavelengths. Okay? So those are emission line spectra. And again, they tell us chemical composition, whether that's on Earth or in outer space. So here is an absorption line spectrum. And here, what you need to do is your cloud of interest, the thing that I'll put a little question mark here. Okay, this is the thing that you want to know the chemical composition of. What you need is some sort of light source behind the thing that you want to understand. So you have light source, the thing you want to understand, and us. Okay, so what happens is, where that question mark is, that's where basically it absorbs certain energies from that light source. So instead of seeing a continuous spectrum from that light source, you basically see bites taken out of it. Okay? So you see where the electrons have robbed energy from that light source to be promoted and are just kind of hanging there. Okay? What's interesting, and I've had other animations that do this, is if we were at another location, let's just say instead of here, if we were over here, okay, looking at this, we could actually perhaps see emission lines instead of absorption lines. Okay, but there we're seeing absorption lines because the cloud is between the source of light and us. So if we look over here, again, we kind of have two different ways to look at an absorption line spectra. You can definitely see the continuous spectra with bites taken out of it, dark line spectra. Also, like I said, if you're into kind of graphs and a number sort of person, again, here along the x-axis we have wavelength, and here along the y-axis we have intensity. So actually here where you see the dark lines, you see the intensity dip. Dark lines, intensity dip. Okay, I would imagine that if you're into astrophysics, studying stellar spectra, probably you're not going to get that pretty picture, you're just going to get the graph, which makes sense. Well, I bet they think the graph is pretty too. So, remember a little bit ago I put E1 and E2? That's what these blue lines are. These blue lines represent energy levels that an electron, specifically an electron around a hydrogen atom, can exist at. So here we're seeing actually that energy would be emitted at these different wavelengths. Okay. The other day I talked about cousins, wavelengths of energy. And as it turns out, I think I got this right. I think I'm on the next slide. These actually would be in the visible region. So these would be visible E, or visible energies. Okay. These longer waves actually would be infrared. And the shorter wavelengths would be ultraviolet. Okay. So we would see those emission lines. If you're wondering what this word ionization is, it's kind of fun. It's basically that particular electron around a hydrogen atom has been left the ship. It's been ionized. Okay. So I think this is okay. So yep, in the middle we have visible, and on either side we have things that are invisible to us. So notice, I think it's kind of cool when things all kind of come together. There's the diagram of the energy levels, but here actually then, notice that you see this emission line right here, okay, this emission line right there, the 486 right there, okay, and the 656.3 nanometers right over there. So this tells us that there is hydrogen there, an emission line spectra. So I actually did a little bit with this slide since I had, since your slides went to print. This slide, I thought it would be good to kind of bring in kind of the negative. You know, this actually is the same element. You see the absorption line, the dark line spectra on the top, the emission line here on the bottom. Okay, notice that they're at the same energies. Those wavelengths are energies. All right. So again, we've seen hydrogen, then you now see helium, sodium, neon. Yeah, that does kind of look like what we saw. Except I'm with you guys. You guys, does this look like what you guys saw? Except there was a green and kind of a blue, kind of faint colors. The intensities may have been less, but they were there. So in this day and age of computers, it's probably easier to crunch incoming data with libraries, with files. It kind of reminds me of a DNA sort of match, okay? And then, of course, this was hydrogen. So back to the sun. The sun, we're used to basically, we send sunlight through a prism and we see a continuous spectra. If you were to actually take a magnifying glass and blow that up, that came through and was your prism spit out, you would see dark spectral lines there. Because just like we looked at the configuration to create dark lines before, we have the sun, which is our source. Then actually the sun has an atmosphere. We're going to talk more about the sun later. But what's in the sun's atmosphere affects stuff that can be absorbed. Okay, so those are absorption lines. So I said that a continuous spectrum without any lines is like a dud, but not really. So there are a few laws of radiation. Okay, remember what electromagnetic radiation are. They're those cousins of energies. One of the things that you probably already know is if you take an object like a poker, okay, a cold poker, and if you poke the poker in a fire, you can actually make that poker turn from black, just minding its own business, to glowing. Anytime something's glowing, you figure it's emitting energy to glow like that. Okay? The color that objects glow, the color that stars glow, actually are an indication of the temperature of that object. So if you've ever heard the phrase, ooh, that's white hot, you know, that's actually true. There's something to that actually something that is white, glowing white is hotter than something that is glowing red in general, unless there's something else working there. So there's two laws of radiation. Okay, there's a law 1 and a law 2 that I'm going to be talking about. Law 1 says that actually when something gets hotter, it begins to emit more energy. So something that's hotter will emit more energy. We're going to kind of see the graph here in a minute, emit more energy. Also, something that's hotter will tend to have a shorter wavelength of what we say the dominant color. I know white, you're like, what color is that? But let's say blue hot. Okay, blue is actually a very short wavelength. Something that's glowing blue is hotter than something that's glowing red. Blue is a shorter wavelength and red is a longer wavelength. So kind of what you just saw a minute ago. Law 1, with regard to something getting brighter and brighter and brighter and brighter, the hotter it is, actually is Stefan Boltzmann's law. Okay. And then the other one, the whole color change, law 2, that's called Wien's law. The whole color change is called Wien's law. So when I up here said, you know, we all saw an orange color from this neon light here. We all saw orange, but if we were to take that light and kind of dissect it, actually that was emitting all sorts of different wavelengths. It's just that orange was what we call the dominant color. Okay? I have some examples to kind of show you that here in a minute. So the dominant color will get a shorter wavelength the hotter it is. So this is why I kind of gave you that mnemonic device, Roy G. Biv. I think it's important that you know when you're looking at colors that the longest wavelength is red and the shortest wavelength is violet. Stars that are red are cooler than stars that are blue. Stars that are blue are hotter. Okay. So right away this weekend you can go and start looking up at stars and saying, hot star, cool star, hot star, cool star. And they'll be like, what? And be like, let me tell you. It's Wien's law in action. All right. So we actually use radiation curves to analyze information coming from objects. So they're called thermal radiation curves. Sometimes they're called black body radiation curves. But here we go. There are on this graph, there are 4 objects. Can you see this blue line here is one object, the yellow line is another object, the red line is another object, and there's a black line over there hiding, that's a 4th object. So they are plotted with regard to what we've been looking at. We have wavelength and intensity. That's the wavelength and intensity. We have short wavelength over here and long wavelength over there. So here's how this works then. The blue line is actually the fingerprint, the information. That whole blue line is the information we would get from a star with a surface temperature of about 15,000 Kelvin. Okay? That whole blue line. We get all that information and plot it. Now, as far as seeing it, it looks like it peaks over in the ultraviolet region of the spectrum. Okay? Our eyes don't detect ultraviolet, so actually we're going to see it as a bluish star. So notice 2 things. We see it's the hottest of the 4 objects I'm going to show you. It's the hottest. So according to the first law, it's like peaking out in intensity. It's definitely highest of these 4 objects. The other thing is the maximum is slid over here to the shorter wavelength. Okay, so let's look at the yellow one. Actually, the yellow one is our sun. When we study our sun, we're going to see that the temperature on the surface of the sun runs about 5,800 Kelvin. So it's cooler. Okay, so notice the 2 things. We see it's squattier, less intense, and we see its peak over there to the longer wavelength. It's a yellow star. Then the third one is another star. So instead of being about 6,000 Kelvin, it's about 3,000 Kelvin. So the 2 things that happen is it's squattier, the intensity is less for all wavelengths, okay, and it is actually the maximum is over there on the longer wavelength, so it would look red. The last one up there is an adorable human, okay, human. So on the Kelvin scale, we run about 310 Kelvin, okay. Now if I were to turn out the light and to watch to see if anybody in here is glowing, you'd be like, no, don't think so. You're not glowing like visible light, but you are glowing infrared, okay? So we can actually make a little fingerprint of you. So notice that this is obviously the coolest object of the 4. So it's really squatty with regard to intensity, and it's definitely over on the longer wavelength. So these would be continuous spectra coming from these objects. So another thing that astronomers are clever to do is to use what we call the Doppler effect or Doppler shift. They're the same thing. There must have been a Mr. Doppler out there because it's always capitalized. So what the Doppler effect does is to make use of the fact that these energies are coming in wave forms. Energies are coming in wave forms. Now this works for light and it also works for sound. So the deal is, in order for the Doppler effect to work, basically the object emitting the light or the sound needs to be moving. The object needs to be moving in order for the Doppler effect to work. And what we call the observer is stationary. So here we have a moving object that's emitting light or sound and a stationary observer. Okay, a source is moving and the observer is stationary. So the EM radiation emitted by the approaching source will be compressed or shortened, okay? So it's almost, you can almost see it, and I actually have some pictures to show it to you. But if, like, I have something emitting light and it's moving towards me, okay, picture the wavelengths, okay, they will be shortened. So literally the wavelengths will be shortened. Shorter wavelengths have consequences. They can, like, move up in color, they can move up in energy. We could have something that was violet be actually ultraviolet, okay? And we see that. We see that here on Earth, and we definitely see that in outer space. So the fact that it's shortened is called a blue shift. So again, the scenario, and I've got a picture to kind of show you. This is where the source is moving towards the observer. And if you're like, oh my gosh, I bet it has to be line of sight, you're right. It definitely has to be what we call a radial motion or line of sight. Okay? So that's called a blue shift. The other scenario is if something is moving, if the source that's emitting the light or the sound is moving away from you. And I can almost see those wavelengths being elongated. Okay, it's the sound or the light information is still getting to me, but the wavelength is going to be longer. So we actually call that a red shift. This is where I always think of the Dr. Seuss book, you know, one fish, two fish, red fish, blue fish. Okay, so the red shift. So here are the pictures I was talking about. In this case, the train is not, it's not sound, it's not light we're worried about that the train is emitting, but it's the sound that the train is emitting. So in this scenario, the train is stationary, it's just oozing sound in all directions, including these two people, okay? So the train is actually going to go to the right. And notice then what happens to the sound waves that the person on the right receives. In that case, the train is moving towards the right. Can you see actually the repeating unit is squished together? So that's actually, in sound, that's not a color or something that would be observed with your eyes. That actually is a pitch. So something that has a shorter wavelength is a higher pitch. Probably a better example, because I don't do much with trains, is just if you've ever been standing somewhere and, for instance, an ambulance is coming towards you. An ambulance is coming towards you. So it has a certain pitch off in the distance, okay, but if it's moving actually towards you, you will hear it kind of, the pitch ramp up, the wavelength shorten, so it'll go as it's emitting its, okay, when it's coming towards you, you'll hear this, the frequency get shorter, and wavelength get shorter, and as it's leaving, it'll get longer. So that was sound, and this is light. Now, granted, that source, which in this case is a light bulb, needs to be going pretty darn fast. But we can definitely see a shift in the wavelength. So, in this case, again, the light bulb, which is the source emitting light, is moving towards the right. You see the guy on the right, he's going to see more of a bluish color. The guy on the left actually is going to see the same light bulb as red. This gets into kind of some Einstein sort of, really, it's like the same light bulb, but, and actually Einstein does have a hand in why this actually works the way it does. So, hurts my brain. Need to read Einstein for Dummies, right? So let's look at the Doppler effect or the Doppler shift in motion. So this would be our library sample. We have nice crisp three emission lines for this particular element. But let's say we go ahead and take the object that's emitting these emission lines and set it in motion. Specifically, what we're going to do first is make it go away from us. Okay? So in this case, you know, if you're pairing up spectral lines, can you see where this one moved over a little bit? They all moved over a little bit. Okay? And the direction they're moving is to the longer. Remember, wavelength is that symbol right there, the longer wavelength. Okay, that must mean that this star, or this source, okay, emitting those emission lines is actually moving away from us. Well, what if we up the speed? Okay, so if we call the first one our library sample A, the second sample B, the third sample C. In C, actually, again, you see those three spectral lines, but they are shifted even more. Okay, so we actually have this Doppler effect indicates how fast it's moving, twice as fast. So let's go ahead and switch gears and compare our library sample to these last two spectra. So, oh yeah, that's cool. So, for instance, let's compare it to, we call this A, B. So A is our library sample, okay, and we have 4 different things to compare it to. So down here, can you see that actually here in D we have moved just a little bit, and in E we have moved a lot. Okay, so E is going even faster. Now, is it going towards us or away from us? Sometimes this makes it to my tests. Actually, you can see that from our library sample, we have a tendency to go to the shorter wavelength. So that must be moving, that's a blue shift, and that must be moving towards. I know, that's terrible writing. I think I've gotten worse. So I mentioned the whole line of sight thing, the Doppler effect or the Doppler shift. When will it work and when won't it work? It will only work if those waves can be compressed or lengthened with this, what we call radial motion, line of sight. So for instance, if that star number 1 was moving, we could know. Let's see, if it's moving away, it's going to give us a red shift, right? All right. Now this star, star number 2, it's got what we call not radial motion, proper motion. So star number 2, you're like, no, I don't see it. You know, I really don't see us being able to use the Doppler effect or the Doppler shift. Star number 2, our best bet is if it's not too far away, we'll actually kind of see it relocate against the background stars, which is possible. Oftentimes, though, we kind of have this sort of scenario, star number 3, which has both kind of a radial component and a proper motion component. So we can get a fix on the radial, but the proper motion is going to have to go about it some other way. All right, on to telescopes. So I brought something to show you today. And this is actually the school's telescope. So I'll kind of say a little bit about telescopes in general. This is, I don't know if you guys can see the mirror down there. Okay. A lot of times students will be like, well, how much did it cost? And that's a really good question. I put in the request for it several years ago, about $2,000. So that's how much they love you. It has a mirror. With telescopes, a lot of times you're like, well, how powerful is it? And a few things give a telescope power. One is how big, kind of we call this the optical tube. This is the optical tube. The optical tube kind of gives you a sense for how big the mirror is or how big the lens is. This one's 8 inches, 8 inches of collecting power. Okay. Telescopes, usually, I think they all must, this is where the heavy lifting is done with that mirror down there. But all telescopes have what we call a sight glass, okay, like a finder scope. So this is the finder scope for this one. The thing about it is this one, it's kind of calibrated so that this finder scope has the same image as whatever's in here. So you can find it in here with a bigger field of view and put it in the center here and it's already in there, okay. So that's a telescope. We'll talk more about what that annoying plastic button is here in a minute, right? The thing about when we're viewing, you're going to see, this is a go-to telescope, so let me kind of show you how that works a little bit, tighten it down. I'll set it up before you get there, or if you are getting there, you'll see me setting it up. And actually, can you hear this? I just love that sound. Okay, there's the verb slew. It's called slewing, okay, yeah. But the cool thing is after I have it set up, it will actually, there's, for instance, an M button here, and M stands for Messier objects. So if we want to see Andromeda, we would go M31, enter. Yeah, and there she goes. Okay, so that's kind of fun.
It'll move and show you that?
What's that?
You press that in, it'll move.
It shows that.
Telescope will move and show you that.
It will.
That's very crazy.
I know, I love it.
That's awesome.
It's awesome. One thing about it is it's gonna be dark out there, so just be careful, after it's set up, if we like bump the tripod too much, then we just need to recalibrate it again. Okay, so it is very awesome. Let's see what else. So what makes a telescope powerful, again, is kind of the whole diameter, which you can kind of tell by the optical tube. But the other thing is, like, usually I tell students the quality. In this case, this is my mirror back here. Here's a mirror right back here. The quality of the mirror kind of gives you the overall sweetness of the telescope. The other thing about the telescope is we will substitute out eyepieces. So this is the end you look in, okay? I actually, with this type of telescope, if I were just to put an eyepiece right there, it gets really annoying. You're limited to where you need to look, where we need to look. So actually, instead of putting the eyepiece there, I have it's called what's it called? I usually just call it the right triangle thingy. What is it called? It's on the box. It's called a diagonal. Right triangle thingy. So this actually then goes into the telescope, and then we have our eyepieces that go in here. And then actually you can turn this any way you want. So that diagonal doesn't do anything with the image other than have a mirror to kind of. So actually, if you see me kind of turning this, if we have kids, sometimes we'll turn it clear down here, like, well, they can see it. Okay, so that's how that works. And there are. I've had friends who, do the whole telescope thing, and they say if you want to really kind of pimp your telescope, you get a new eyepiece. So these are eyepieces. Yeah, I know. So I've had the school buy kind of an assortment of eyepieces. This is an eyepiece that actually, I'll pass these around. This one, I think it doesn't say something about planetary, but this one's for planets. Okay, so they kind of, and as they come around, you kind of feel the difference. And this one probably costs, I don't know, maybe $70. That one cost about $250. So I think, I can't remember. They were generous. It's when they were actually spending money on things. So eyepieces. So throughout the night, we'll swap out eyepieces. Okay, so that's kind of fun, right? I'll just kind of swap them out, and it will look different. It will usually change the magnification. Now with the moon, I also want to show you one thing. I'll pass this around too. But with the moon, we actually have, here's the box that came with it. The moon can be so bright, oh my gosh. This first note here says telescopes are photon buckets. Basically, they take all the light that's coming in this shaft, 8-inch diameter shaft, and concentrate that light to a point. Now, if you're looking at the Andromeda Galaxy, you're counting on using all those photons. If you're looking at the moon, not so much. The moon is so bright to your eyes. So what we have is, this actually is for the moon. And one of the things I didn't emphasize about light is light does this, and light actually then is kind of directional. So what this does is make use of that point. We basically polarize light in one direction, and it can actually be dampened down. But my point is, as this comes around, go ahead and see if I can do it just like this. You can see the green, and I'm going to kind of rotate it a little bit and look at the intensity. Now it's purple. Now look at the intensity of the purple. Okay, I'm just twisting it. If I twist it, okay, that basically blocks out all of the light. I'm going to keep twisting it again, okay, and the light's going to come back. So what we do basically is put this in line with the eyepiece, and so we can use it as to dampen the light down. Okay, so if we're out there looking at the moon, hopefully on Thursday, with this telescope, say, Mrs. Snipes, did you put your little thing in? Because that's pretty darn bright. Okay. When you're out there looking through any telescope, and this one included, sometimes everybody's eye is a little bit different. You need to focus it. So the focuser here is, and I'll remind you when you're out there, but the focuser here is right here, and so you kind of get it just right for you. Are there any questions about telescope?
Does the school just have one of these?
The school actually, thank you.
Yeah, take these away from me before I break them.
This is the newest one. The school has one that still seems to work, but it was kind of acting up, and I don't know how old that one is. So we have two. But we'll just have one set up, I think. I've got a telescope that, and it breaks my heart to talk about it right now. I have my own personal telescope, and it's from Celestron, and if Celestron's here listening, they suck. But anyway, I'm so mad at them because I love my telescope, but it's in for repair. My mount part is in for repair. And it's been there since July 5th. Let me tell you, I'm one mad person. I sent them an email today saying there's a lunar eclipse coming up. I'm just saying. You know, I want my telescope back.
Kind of like to have that.
I would, and I don't know if they're going to come through or not. I thought about going on Twitter because you do hashtag and just doing hashtag Celestron and talking smack. Well, I don't
Do
know.
that.
I'm kind of scared
Go there and talk some major.
because they look for those hashtags. I don't know. So, but on my other telescope, if I bring it out, it's like a long one. It's not. It doesn't use mirrors. It uses a lens. So it's the other type of telescope. Any other questions? No? Okay, so just a little bit about telescopes. They gather all the photons that are landing on the mirror or the lens to one spot. We're going to call that the focal point. So they allow us to gather that light, concentrate it so we can see things more brightly. We can see detail on things. And I mentioned how good is your telescope? Well, there's something called angular resolution we're going to talk about. And basically that's, does your telescope brighten things, but can you see crisp detail things? Like if you have good angular resolution, you can actually look at the planet Jupiter, which has bands, actually it has cloud bands, and you can actually see the cloud bands, and even swirls in the clouds maybe, if it has good detail. The other thing is that it allows us to see distant objects, like the Andromeda Galaxy. Right now with your naked eye, if the skies are pretty dark, you can actually see a fuzzy patch with your naked eye. And then you get binoculars and you look at it, you're like, oh dude, that is so M31, okay? So it allows us to see things that are farther away. So the two types of telescopes, this is the reflecting telescope, okay? So it uses mirrors. Here's an example of a reflecting telescope. So like I said, the light travels down the optical tube to the back, okay? And I have an image that we'll probably get to on Monday. And it bounces off the back. Oh, it's right here. Okay, see it's coming down, okay, to the back, and it bounces off the back, and it goes up to that annoying button, that plastic button. That's that plastic button right there. Okay, we call it a secondary mirror. Okay, and basically from the secondary mirror, it comes back and it finishes gathering to the focal point right here. Now there's like 4 designs of telescopes that use mirrors. This actually is called a Cassegrain design. So this is the secondary flat mirror right here. And this one right here is actually, this 8-inch mirror back here is what we call a parabolic shape. It's a concave, okay? So that's kind of how that works. And then, so it comes back here, it goes to there, and then it goes back out. I call this the butt. It comes back out the butt. One of the things that you think, well, it's okay. I like that butt. Okay? So my telescope that Celestron is fixing, or actually not the tube, but the mount, is this other type. It's a refracting telescope. And this one, I tell kids that come to the observatory, it's like if you wear glasses, it's very much like what your glasses do. Your glasses are correcting the light that comes in so it hits the back of your eye correctly. And so that's what these refracting telescopes do. At the Whitty Observatory, which I hope you get there once this semester, they have a refracting telescope that has a tube that I think is 30 feet long. Maybe 30, 15. I don't know, it's very long, very beautiful, okay? But basically at the end of that tube is a lens that gathers light to a focal point. Okay, so the focal point for refracting telescopes are behind the lens. For a reflecting telescope, they're kind of in front of the mirror. That's how that goes. Well, I think that's a good spot to start. I think we're in good shape. There won't be any homework due Monday. We'll finish up this chapter and the next chapter for your unit exam. Any questions? All right.